Okay, now let's look on to track initiation. A track is usually initiated after the detection of 3 or more scans, which I said previously, to prevent excessive false tracks from being established. And these detections are checked for consistency of motion along a reasonable trajectory and velocity profile for the targets of interest of the particular radar, be it a radar that wants to surveil and track missiles or aircraft or what have you. A clutter map may be used to prevent track initiation in areas of strong clutter echoes not suppressed by Doppler processing. Clutter map may be used to keep track of large bird echoes so they may not be reinitiated on them. And I know several radars that do that when they'll have even an individual large goose flying through the coverage. They will keep in a map that target in track, tracking it at its 30 miles to 40 miles an hour land speed, or 60 miles an hour. You can remember the wind can be coming at the radar. You have to remember the radar measures ground speed. And so the wind can be coming against the bird. It's flowing this way. And so the Doppler can be relatively small and relatively large, excuse me. I got that backwards. The bird can be flying along, flapping its wings at 30 miles an hour and have a wind in addition at another 35 miles an hour or 40 miles an hour. And that can be equivalent in real velocity or speed of an aircraft coming slowly into land with an opposing wind. So you have to keep bird echoes like this, and a lot of the time, some radars do it, in a clutter map. Military aviation often have requirements that demand quicker track initiation than air traffic control radars, which run at 4 to 12-second scan rates. And they have high-speed, low-altitude targets that break the horizon at short distance. And the issue is mitigated by using phased array with variable update rates, as I mentioned before in that block diagram. And the track initiation in dense clutter environment can be quite demanding on computer software, hardware, and the brain power of the analysts who develop these algorithms. Now let's look at track association. Remember, that's only one of the 6 issues. First, new detections are correlated with predicted positions, existing tracks. And here we have predictions from existing tracks. As you would expect, this would have been the first detection, the second scan, the third time you looked. And here would be the 4th one. They look like they're about the same velocity. Here's where you'd expect it to be. What you do is you set up a tracking gate around where you expect the detection to fall and look and see if you have a new detection within that gate. And this would be assuming a constant velocity. Is this position consistent with the velocity of the established track? The track gate should be large enough to be consistent with noise estimates, because there'll be noise estimates on azimuth and elevation, but small enough to minimize false alarms within the gate. And maneuvers of targets pose a more difficult problem. And we're just going to state that now, but we're going to go into that more. And false alarms may be within the tracking gate because of birds. You may be traveling through an area where there's clutter breakthrough. You didn't quite have enough subclutter visibility. There was a tip of a mountain, and you're getting some false alarms from the mountain. And you've got a target within the predicted gate, but that target could be a single-engine aircraft which can maneuver. And so you have what we call a maneuvering track gate, which we also use for targets that can maneuver. And then we look and see, is there anything in the maneuvering gate that might give us a problem? Like, in other words, this target is in the gate, but actually the real target is over here and is heading off in that direction. So false alarms may be in the tracking gate, and one of the things you can do is bifurcate the track. In other words, say, gee, we've got this track and that other one, and so you can have set up alternates and see which one pans out, and you pick one as we think it's the best, and then if these don't pan out as having more detections, you don't have to show them to the operator. Now, again with association, things can get even more complicated. If the association is successful, the track files are updated, and we have a new target detection data. Two targets may cross, confusing track association. This is usually a good way to test a tracker, and this problem is usually solved with multiple hypothesis testing. In simple words, which pairing of the detections in the overlapping gates are more probable? And so that means we want to have a very accurate knowledge of the predicted position of where in the tracking gates each one would fall. The criteria might be the proximity of detection to the predicted positions, similarity of radar cross-section to the detections of those tracked. This might be at a much higher altitude, a Boeing 727, here, which would have a large cross-section. And this might be a single-engine Piper Cherokee down at 10,000 feet, where this is at 30,000 feet. And you could tell from the difference in radar cross-section right away that would be with each of these, which one was which. And the similarity of the velocity of the detections to those of the tracks, which would be different, of course, from a single-engine plane or a jet engine plane operating at a much higher speed. And the similarity of the track length to the detection of similar tracks. So we have this issue of resolving them. Now, I've alluded to several different times, how do we get the best filtered estimates of a target's present position in velocity and position? Where is it now really from the history? And using this estimate, predict the location on the next scan. And the simplest method that's used is what's known as an alpha-beta tracker. It calculates the present smooth position of the target and velocity. And in one dimension, this is the smooth position, and this is the measured position on the nth scan, and Pn is the predicted position on the nth scan. There's alpha, and then there's the difference between the two. And so we smooth it. And the smooth velocity is this. Thus, the nth scan, on the nth scan, the predicted position is given by this. So in the next predicted position, we take n, and these are with bars, the smoothed, and the dot means it's a velocity. And so what we're just taking, it's the predicted position on the next scan is its predicted velocity that it was measured on the last scan, the smooth, that times the time between scans. And that will give you the predicted position. Okay. Now here are those two equations. When alpha and beta are 0, the smooth tracker information is the current target data, is not included. The smooth data is more important than the calculating the predicted position, and they're closer to 0. The closer they are to 0. So when they're small or 0, the current target position isn't included. You just take what you get. When alpha and beta are 1, there's no smoothing of the data. The current position of the data is more important, most important, and it's more important when they are closer to 0. Now, if acceleration of the target is present, these filtering and prediction equations can be extended to produce an alpha, beta, gamma filter. And here would be how we'd predict ahead with those equations. Now, maneuvering targets caused errors, transient errors in alpha beta filters. If x sub n is the true target trajectory and x sub pn is the predicted target trajectory, and we run this through a typical alpha beta filter, the transient error between the true position and the predicted position, you can see, you asymptotically approach it. And the transient errors result from an abrupt step in the change in velocity. So these transient errors will result. But it will, after a while, come on to it. Now, maneuvering targets can be handled in many different ways of adjusting, of knowing the accelerations you expect. And with airplanes, the pilot will usually turn, a 3G turn. And so it's a pretty, if it's a very slow turn, you'll see it coming from one scan to the other. But if it's a fast 3G turn, if it's a half a G turn, it'll see it slowly coming and you'll track it right easily around it. But if it's a very fast 3G turn that's at a limit, then you're going to have some trouble with the state vector that you predict not being exact. If the previous ramp trajectory is a reasonable approximation to the angular change in direction of the target of the steady state noise error is minimized if beta is alpha squared divided by 2 minus alpha, and that's called the Benedict-Bordner equation, and it gives you a constraint on alpha and beta. And the optimum values of alpha and beta are determined by the bandwidth, the range resolution, and other radar system factors such as the maneuvering capability. One can select alpha and beta based on least squares fit to the track data, and that yields these numbers, where these are the numbers of observations that are n of the number of observations used to do a least squares fit on the data to develop. Another approach, the parameters alpha and beta cannot be made to adaptively, can be made to adaptively vary as the target does or does not maneuver. Okay. And when you're doing this fitting, you have to have n greater than 2. Now, Bar Shalom has noted in his text that a commercial airliner which can perform a 90-degree maneuver in 30 seconds, that's a turn rate of 3 degrees per second, it will detect by a radar just 3 times. And that's a difficult task for long-range air traffic control radars. Fortunately, when you're away from the terminal area, they rarely, if ever, take such drastic turns. And in the terminal area, which is 60 miles from the airport, usually it's less. It's about 40 miles, and the ASRs overlap congested population centers. So that typically one radar is looking out to 40. They're seen by airport surveillance radars at a 4.8 second data rate. And on the other hand, if you've got a military fighter aircraft, they can execute up to 5G turns. As one would expect, military radars have much higher track revisits rates, and many of these are phased array radars with appropriately high track update rates. I can't discuss this view graph without mentioning to you a real-life experience that happened to me, my then 2.5-year-old son, and my wife, who was 3.5-year-old son, and my wife, who was pregnant with our youngest son, Andy. We were coming in on a very clear day on a company aircraft. This was when I was not working for Lincoln Laboratory. We don't have company aircrafts. We did at Lincoln Laboratory. And it was a twin-engine turboprop, clear as a bell. And we were about at 3,000 or 4,000 feet on a perfectly clear gliding approach in Lancaster County, Pennsylvania. You can just see the beautiful cornfields, flat as can be. And then I'm looking out, I'm sitting in a seat that is facing to the rear, and I have a window about that big. And I'm just looking out the window, and all of a sudden, at least this is my remembrance, another single-engine aircraft literally almost fills up the entire window, which is a foot away from me. This is clear day. And I hear the two pilots, which are a mere, just have a little, the pilot and co-pilot just have a cloth between the passengers and the six people, the four of us on the plane. I hear them yell expletives. Oh, expletive. And their plane took, I know, the hardest lower left turn it could possibly take. And it turned out that other aircraft, on a clear day, did not know that it was on a collision course to hit us. And I am alive today because I don't know whether it was the pilot noticed it or a radar nearby noticed it, or one of the pilots probably did look outside and back as they were coming in and noticed that they heard an engine or something. But it saved my family of not my first son and daughter, but my second two children and my present wife. We would not be here along with one of my good friends, because you only make one mid-air collision like that. And anyway, that's my 2 cents worth on mid-air collisions. I love to have radars that work very well and can tell the air traffic controller, even when they're flying under visual flight rules, which we certainly were, that they have transponders too, backing it up, that one plane is coming to intersect another. But in any case, we'll move on. Now we're going to discuss Kalman filters. As opposed to an alpha-beta filter, a Kalman filter intrinsically is capable of dealing with maneuvering targets. It's part of the nature of the formalism that it's set up. You input into this filtering process a model of the measurement error, the target trajectory, and its errors. That is the equations of motion, the forces on the object, gravity, atmospheric forces, the trajectory uncertainties such as atmospheric turbulence and unexpected maneuvers. Certainly, range instrumentation radars that deal with measuring missile trajectories in the atmosphere are very, very accurately want to track targets on ranges would use a Kalman filter. And the Kalman filter reduces to an alpha-beta filter for Gaussian white noise and a constant velocity trajectory, alpha-beta, and they're computed sequentially by the Kalman filter. Skolnick notes in his reference one, and it's well said, the Kalman filter has much better performance than the alpha-beta tracker since it utilizes more information. Others have noted the same reference, and it should be noted that it's much more computationally intensive than an alpha-beta filter. Here's a two-state Kalman filter from Eli Bruckner's book, reference 6, Tracking and Kalman Filtering Made Easy. And here it is. It's a solution. The solution's an alpha-beta filter with weights, alpha sub n and beta sub n, that vary with scan number. And also, here is an alpha-beta gamma filter in Eli Bruckner's notation. Okay, now we're going to take a break. We're about halfway through the view graphs in Lecture 16, which is Part 2 of the whole parameter estimation tracking thing. And tomorrow I hope to record that stuff.